Good morning, this is your Stat Sensei, Mr. Spensei, and this is Death Packet Problems on chi-squared and regression. Specifically, this will be the chi-squared problems. We're going to be working on problems 111 through 120. So polling organizations regularly collect data on the public's opinions and habits. A question on a recent survey asked, how often do you purchase coffee from a coffee house? There may be differences in how people respond to this question based on whether the person is a full-time student. Suppose a polling organization uses random digit dialing of local phone numbers to take a poll and ask respondents whether they are full-time students. In addition, they ask respondents to identify how often they purchase coffee from a coffee house, never, once a week, two or three times a week, um, daily, more than once a day. The data are collected by a 5 by 2 table of counts. By the way, so we know we have a 5 by 2 table of counts. And also I wanted to point out it's only one sample with multiple variables. One sample with multiple variables tells me this is a chi-squared test of independence. Um, which of the following is the appropriate null hypothesis when conducting a chi-squared test for the data? All right, the proportion for each category in the 5 by 2 table will be 10%. We don't know that. They didn't say that it would be equal. All right, so we don't know that. For each purchasing frequency, the proportion of full-time students is different. That might be something we have for an alternative. That's certainly not a null. How often a person purchases coffee from a coffee house is not associated with whether the person is a full-time student. Well, we said this was going to be a test of independence. All right. And so in a test of independence, we need to identify what our variables are. Well, our variables are whether they're a full-time student, that's variable one, and variable two is how often do I purchase coffee? And that's variable two. All right. Now, this one has two choices, full time or not. This one has multiple choices because they had never, once a week, two or three times a week, daily, more than once a day. So one, two, three, four, five. So this had two choices and this had five choices. All right. So they want to know if it's a test of independence. So they're basically saying our full time student and per sorry about that. That was a bell. Full-time student and purchasing coffee, are they independent? And remember, the null is always independent. And the alternative is not independent. But we don't always say it that way. Sometimes, instead of independent, we say not associated. And over here, it is associated. All right. Now, I always like to use the positive and say, hey, it's independent, but the same as being independent is not associated. All right. Um, so in this case, they said how often a person purchases coffee from a coffee house is not associated with full-time student. How often full-time student? So we have the two variables, and they say it is not associated. Well, that's what we would have for our null hypothesis. So the answer to 111 happens to be C. D, 112. Excuse me. So 111 is C. For number 12, 112. How are expected counts calculated when a chi-square goodness of fit is conducted? Well, chi-square goodness of fit, we're going to have to take the sample size and multiply it times the probabilities of the null hypothesis. It'll be n times p, n is the sample size, times each one of the probabilities in the null hypothesis. So the expected counts are calculated by multiplying each proportion in the null hypothesis by 100. That's only true if n equals 100, and we don't know that it does. That's probably not the right answer. The expected counts are calculated by multiplying each proportion in the alternative. No, it's not based on the alternative. It's based on the null. The values observed from the sample are the expected counts. No, those are the observed values. Those are not the expected values. Remember the formula for the chi-squared is observed minus expected squared over expected. The observed values are the O, and we're looking for the E. The expected counts are calculated by multiplying each proportion in the null by the sample size, and that's what we have here, n times the proportions. So the answer to 112 is D. For 113, a survey was conducted to investigate whether there is an association, all right, between a person's age and their thoughts on what a state senate should do about state parks. So, um, participants selected from leave state parks the way they are, increase fundings, or completely overhaul the parks. And their ages were categorized as under 30 to between 30 and 50 and over 50. The hypothesis test statistic was calculated to be 15.01, which of the following is the p-value of the test. All right, so in order to calculate the p-value, I need to know the degrees of freedom. And degrees of freedom for a goodness of fit is just categories minus one. But in this case, we're looking for association. So this tells me it's a test of independence, and degrees of freedom is row minus one times columns minus one. So I need to figure out how many different things I had for each. So participants selected from leave parks the way they are, that's one. Increase funding, that's two. To completely overhaul the state parks. Doesn't matter what I put in the rows and what I put to columns. I'm going to go ahead and use that for rows. So I have 3 minus 1 because I have 3 different groups for that one. For my columns, I have their age category under 30, that's 1. Between 30 and 50, that's 2. And over 50, that's 3. So I also have 3. So this is also 3 minus 1. So 3 minus 1 is 2. And 3 minus 1 is 2, and 2 times 2 is 4. So I ended up with 4 degrees of freedom, at which point I can go to the calculator and go a second vars and scroll down to chi-squared, CDF, and my lower bound, because keeping in mind this is a chi-squared, so being a chi-squared, it's skewed, starts at 0. I have a chi-squared value of 15.01, and it's going all the way to positive infinity. So with that in mind, my lower bound is 15.01. My upper bound is 9 raised to the 99th, and my degrees of freedom happens to be 4. And I end up getting 0.0046. Well, the closest answer to that is A. So the answer to 113 should be A. I'm going to do that in red so it shows up. Okay. All right. So that's that one. Next one, 114. A state political analyst wants to see whether there is an association. Okay. So this tells me a test of independence between the region where a person lives and whether the person is in favor of increasing the state gas tax. A random sample of 270 residents was taken, and a random sample of 270 was taken, and the table below shows the results from the survey. Which of the following is closest to the p-value, to the appropriate p-value of the test? Whether there's an association between the region where a person lives and where the person is in favor of increasing the state gas tax. So I have a couple things I can do. I could actually run the entire test and show you all the work, but I'm going to go ahead and do it the way I would do it if I'm doing multiple choice. So I need to ignore the totals and focus on this. So I look at this and I'm going to basically have a 2x3 matrix. So here's what I'm going to have to do. I'm going to have to go blue button, and I'm going to go to the matrix button on my calculator. I'm going to arrow over to the word edit, and I'm going to put 2 enter, 3 enter, and I'm going to input the data 38, 42, 51, 27, 62, and 50. I want to make sure that I have that in there correctly. Looks like I do. As soon as I have that, I'm going to quit. So blue mode, I'm out. Now I'm going to go stat, test, and I'm going to go chi-squared test. Now, technically, I have not put in expected in an ask form, but that's okay. It's going to go ahead and calculate the expected for me. Now I'm going to press calculate, and I get a p-value of 0.0644, and they asked me for that p-value, which is 0.0644. I want to go back real quickly, just in case you're struggling with this, and go, well, in degrees of freedom in this case, while I'm here, we have 1, 2 rows. So we have 2 rows, and we have 1, 2, 3 columns. And so rows minus 1 times columns minus 1, that's my degrees of freedom. So 2 minus 1 times 3 minus 1. 2 minus 1 is 1. This is 2. 1 times 2 is 2, and that's where I get the 2 degrees of freedom. So the degrees of freedom equals 2. Now, I want to show you, go back to my matrix. I'll go blue matrix, go over to edit, and I'm going to drop down to letter B and press enter. And look, I didn't enter letter B. It calculated my expected values for me. So it already automatically did that had they asked me for it. All right. I don't know how to say this, so please forgive me if I'm mispronouncing it. Snoqualmie is a name shared by a waterfall and a tribe of Native Americans. In a study of the cultural importance of the waterfall, 2 of the Snoqualmie tribe were randomly surveyed. One group consisted of Snoqualmie members living less than 25 miles from the waterfall. Another group consisted of Snoqualmie members living more than 25 miles from the waterfall. So that gives me the two group, more than 25, less than 25. The researchers asked each member to rate the cultural importance of the waterfall as low, medium, or high. All right, so there's our low, medium, high. And data is shown in the table. If the distribution ratings are the same for those Snoqualmie members living less than 25 miles from the waterfall and those living more than 25 miles from the waterfall, which of the following is equal to the expected count of members living less than 25 miles of the waterfall and who rated the cultural importance as high? All right, so let's identify which group we're looking for. Less than 25 miles. All right, so that means we're looking at this column. Who rated it cultural importance as high. All right, so what I'm going to need in order to do this is find out my my column total and my row total. And basically it's going to be row total times column total over total total. Well, my row total is 17. My column total is 50. And the total total is 88. So 115, the answer choice, 70 times 50 over 88, my answer choice is E. All right, hopefully that helped with that one. Number 116. A hypothesis test was conducted to see whether there is an association, so this is a test of independence, between a person's income level and his or her education. A random sample of 225 people was selected, and the appropriate test was conducted. The chi-square testing and corresponding p-value were approximately 13.36 with the p-value 0.01. Which of the following is the correct interpretation of the p-value? All right, so this is a test of independence. So what's a test of independence? Test of independence says that the null is independent. So our HO is independent. Independent, which is not associated. The ha is not independent, which means they are associated. Okay. And what are they talking about being associated? Um, the association between a person's income level, that's one variable, and the education level. So are income level and education independent, or are they not? Well, they're asking for the p-value. The p-value says, hey, the p-value is given that they are independent. Given that they're independent, the likelihood we get a probability this extreme or more is 0.01. So assuming that the person's income level and education are independent, hey, that's the first part. There's a 1% chance of finding a test statistic of 13.36 or greater or more. All right, so our answer to 116 is specifically A. 117, a political analyst wanted to see whether there's an association between political affiliation and where a person lives. The analyst took a random sample of 1250 in a state and asked them which political party they were affiliated with and what county they lived in. The following are the hypotheses the analyst tested. There is no association, which is the same as saying it's independent. All right, so this is the same as saying independent between party affiliation and county. There is an association, which means that's the same as saying not independent. All right. The chi-square test statistic and p-value were 19.78 and 0.003. All right, that's a pretty extreme p-value. That tells me I'm going to reject the null and say that there is an association. So there's convincing statistical evidence to suggest that political affiliation and where a person lives are independent. No, we rejected because this one was the independent. We're rejecting independence. There's convincing statistical evidence to suggest that political affiliation and where a person lives are dependent. That's kind of right. But we don't like to prove the alternative. We don't like to prove the alternative. We're just rejecting the null. So I don't really like this one. I'm going to put a question mark. I don't really like this one. There's convincing statistical evidence to prove that political affiliation and where a person lives are dependent. We never prove anything in statistics, so that one's completely wrong. There's not convincing statistical evidence to suggest that political affiliation and where a person lives are independent. So I don't like this one. By the way, am I reading this all correctly? All right. And then there is not, no, we have convincing evidence. So the nots are wrong because we have convincing evidence. So let's go back to this. There is convincing statistical evidence to suggest that political affiliation and where a person lives are independent or are dependent. So we rejected independent and we believe this. That is my best answer. I much prefer it said there's convincing statistical evidence to say that they are we're rejecting this, but this is my best answer because these can't be. All right. So the best answer to 117 is B, not the greatest question. All right. 118. A chi-squared test of independence was conducted to investigate whether there's an association. Okay, all right. So we're doing a test of independence between where a person lives, north, south, east, or west, and who the person planned to vote for in the upcoming mayoral election, the incumbent or the challenger. A random sample of 100 potential voters was selected, and the hypothesis test had a chi-square test statistic of 0.02. Which of the following is a correct interpretation of the p-value? But once again, we need to talk about what it is. So the null, as I said, they're looking for association. So that tells me it's test of independence. So my null is they're independent, IND, which means they're not associated. All right. The ha is not independent, which in case they are associated. All right. Well, the definition of p-value is the probability of getting a test statistic this extreme or more, given that the null is true. So, given that where a person lives and who they're voting for are independent, is what we're looking for. All right. There's a 2% chance that where a person lives and what they plan to vote for are independent. No, it's given that those two things are independent. There's a 2% chance we get a test statistic like this. All right. There's a 2% chance that where a person lives and what a person votes for are dependent. No. There's a 2% chance of making a type 2 error that has nothing to do with it. Assuming that location of where a person lives and who the person plans to vote for are dependent, there's a 2% chance of finding a test statistic that is 9.84 or greater. This is really close, but we're not looking for dependent. We're looking for independent or not associated. It's either got to be independent or not associated. Didn't say that. Assuming that location of where a person lives and who that person plans to vote for are independent, there's a 2% chance of finding a test statistic that is 9.84 or greater. So our best answer to 118 is E. All right, 119. A college administrator wanted to know if the proportion of students who request online classes, lab classes, or lecture classes was different at two campuses. So we're looking at two separate campuses. At each campus, the administrator took a random sample. Hey, we have two random samples. Because we have two random samples, this is a chi-squared test of homogeneity. All right, so we're looking at a chi-squared test of homogeneity because we have two samples. 250 students at each class they preferred. The conditions for the appropriate test were verified, and the chi-square statistic was calculated to be 4.0 with an associated p-value of 0.1347. If the significance level of the test is 0.05, what conclusion should the college administrator make about the proportion who request on uh, line lab or lecture classes? So first off, let's look at that p-value part versus the alpha. All right, so our p-value in this case is 0.1347. Our alpha is 0.050. So this is definitely greater than, so our decision is to fail to reject. The fact that we're failing to reject means there's not convincing evidence. So this convincing part, we don't even need to read. We saw convincing, it's not. All right. And what are we caring about in this case? Well, when we're talking about homogeneity, we're talking about the proportions of the two samples being the same. So so our null hypothesis for this is HO, the proportions are the same for the two campuses. The HA proportions are not the same. So there's not convincing statistical evidence to suggest the proportion of students who request certain classes is the same. No, there's not statistical evidence to say that they are not the same. So moving on. Um, There is not convincing statistical evidence to suggest that the proportion of students who request certain classes is different. Yes, we can't say that it's different. We can't say not the same because we remember our statement is always about the alternative at this point. It's like, no, we failed to reject the null. There is not sufficient evidence to suggest that the proportion of students requesting certain classes is not the same, or in this case, is different. Because remember, different is the same as saying not the same. Best answer choice to 119 is D. All right, 120. A random sample of 300 United States cell phone users were asked their age in the question, do you regularly use your cell phone to text while eating dinner? The number responding yes was tabulated separately for young adults aged 18 and 29, older adults 30 to 64, and elderly adults. So we only took one random sample, but yet we have multiple groups. All right, the fact that I have multiple variables, I have an age group, and I have a cell phone texting group tells me this is a test of independence. One sample can either be goodness of fit or test of independence. This has two variables. Goodness of fit only has one. So, which of the following would be appropriate hypothesis to investigate whether the survey provides convincing statistical evidence that there is an association? All right. So remember, if it's when we're working with test of independence, the null is independent, which is not associated. The ha is not appended and associated. Okay. So the order really matters. They are independent, which means they're not associated. They're not independent, so they are associated. So the null, the sample proportion of adult cell phone users who use their phone for texting while dinner is the same in each group. I don't really like that because this is talking about proportions, and this sounds a lot more like a chi-squared test of homogeneity, and we're working with a test of independence. And the reason I know it's a test of independence is I have one sample, two variables. All right, one sample, two variables. To be in homogeneity, I would have had to have two samples. I don't have that. This is a homogeneity. That's not correct. Among adults in the United States population, there is no difference between age group and the proportion. Oops. Once again, we're talking about proportion, and that sounds a lot more like either a chi-square goodness of fit or a test of homogeneity, and we know we're working with a test of independence. For this sample of the United States population, there is no association. Well, that's starting to look good because we want no association for our null between age group and cell phone usage. That sounds good. For this sample, there is an association between age group and cell phone usage to text while dinner. That's looking pretty good. Right? So I'm kind of liking 120. C, going on. Among adults in the United States population, there is an association. No, it has to be not associated. Among adults in the United States, there is no association between age group and cell phone usage um, uh, to text while dinner. And then among adults in the United States population, there is an association. So I like C and E. So let's look at those real carefully. Well, this one says for the sample, oh, we don't do it for the sample. We do it for the population. All right, so C and E are very similar, but it's E because we don't do it for the sample, we do it for the population. All right, I hope this helped with this, and I look forward to seeing you on the next one. Thank you.